try with stuff, you can backtrack if you've really made a mistake and so on. So there are all these heuristic algorithms that in practice work out pretty efficiently. So coming up with really difficult instances of SAT is actually kind of challenging. Okay? So that's why even though we don't know of any algorithm that is guaranteed to run better than 2 to the n. So in practice, you can often, if you have a SAT formula, you can try to see if it's satisfiable or not. So because formulas have structure, and so maybe I should just mention this one point. Okay, so this is something that I wanted to do at the very end of the course, okay, which is that many problems, when we study about them in theory, we study about the worst case complexity. Right? So we always say, okay, so what is, I want an algorithm that has this running time on every possible instance. But sometimes you don't care about every possible instance, right? So you have an instance of a problem and that's what you want to solve. Okay? So, and your instance may have some structure. So there are all these, you can always say, okay, if I had structure like this, can I solve it faster? Okay, so this is what is called beyond worst case analysis, and you'll see that in the very end of the course. Okay, but so SAT is one of these problems where, in some sense, very unstructured, like random formulas are very difficult to solve. But if you have structured instances, there are actually known good algorithms. So that's generally one point related to what you're saying. Okay, but SAT has heuristics that often work pretty well. And this 1.4 to the n is an algorithm of similar kind. So if you have 3 SAT formula, then you can try setting one variable to be one or the other, and things will simplify. Alright. So I said that SAT is a fundamental question in CS. Okay, and why is it so significant? And last time we said that essentially it captures this notion of, can exhaustive search be avoided, right? And in some sense, if you take this circuit viewpoint, then we are essentially saying that we are asking the question, do there exist inputs to a circuit so that the final answer comes out to be true? And many problems you can think of can be phrased as circuits, right? Like, so in your homework you're going to see, this is actually a very trivial homework, but you're going to see, for instance, Sudoku. Okay? So you've got to fill in every square, and every square has some number in it. And you have some constraints, right? Like every row has to have a certain thing and so on. And each of these circuits you can, each of these constraints you can think of a circuit actually checking if that constraint holds or not. You want to ask, is there a global assignment so that in the end all these constraints are satisfied? So what you have is an AND of a bunch of constraints. Okay. And so many problems you can actually phrase it like this. Okay, so you can come up with a circuit and the answer tells you if it's a valid thing or not. Now your question is to actually determine an assignment that makes this thing true. Right? So for this reason, P versus NP problem is very significant. Okay? And last time I also told you, for instance, mathematical proofs can be written as some kind of a satisfactory thing. Because you can say, does statement 2 follow from statement 1? Statement 1 follow from the axioms and so on. Okay? And this can also be phrased as some circuit that you're essentially, and the proof that you write down is essentially the input to the circuit. So this is why it's a fundamental question. Okay. But yeah, so we believe that the answer to this is no. Okay, so we believe that P is not equal to NP. But this is one of the biggest open questions in computer science. Right? So we don't know that P is not equal to NP. So you would guess that there is no way you can actually find out if there's a satisfying assignment in polynomial time. Right? Polynomial is the size of the input. But we don't know how to prove this fact. Okay, so this is what's called the, but we don't know how to prove it. So in fact, the situation about this problem is so embarrassing that people don't even know that if you have a SAT formula and n variables and m constraints, then you can't solve it in something like n plus m times log n plus m. So we don't even know that that is not possible. It's something almost linear. Right? So that's why, I mean, even though the best algorithm is something like 2 to the n, we don't even know that this is not possible. Okay, so it's really difficult to prove lower bounds. Okay, so this is why we get to reductions. Okay, because we say that, okay, I don't know how to, no one really knows how to prove lower bounds. So at least we'll try to, reduce between problems, right? And say that, oh, this problem is at least as difficult as the other, and SAT is something that no one knows how to solve, therefore my problem is also difficult. Okay, so that's what we do in complexity. And yeah, so this is the idea of reduction. Okay, that if SAT cannot be solved efficiently, and there's a big if here, so we don't know, right, then neither can problem X. Okay, so this is what we started looking at last time. Okay. And the first cut that we said is what we call Turing reductions. And we want to say problem B is at least as difficult as problem A. And then we said that the way you can prove this formally is by saying, suppose we have an oracle M for solving B. Okay. Then you can solve problem A also in polytime using function calls to M. Okay, so this is one natural way you can prove that problem B is at least as hard or harder than problem A. Right? Because if I can solve, we're trying to say problem B is more difficult than problem A. Means that if you can solve B, you can solve A. Right? That's the intuitive meaning. And how do you formalize it? You formalize it just like that. Right? So you say that if I have an oracle M for solving B, then by making polynomially many function calls to that oracle, I can solve A. So yeah, think about it for a bit, because it can be confusing which way this reduction is going, right? So that's often the confusion. So you can also, some people like to think of harder than, some people like to think of easier than. Right? So you can always phrase it as saying problem A is easier than problem. This is like saying if I can solve B, if there's some algorithm to solve B, I can use it to solve the problem. So we'll see some trivial examples of this. So first, this one we call reducing problem A to problem B. So this is the notation. Reducing problem A to problem B. This is what we mean by that. Like intuitively we want to show that problem A is easier than B. And let's see some examples. Okay. So satisfiability is a problem we know. We are given a formula phi and we want to know if there exists some set of inputs that make the formula true. And that's satisfiability. And unsat is the negation. Okay, so the negation of this is it true that for all xi, phi is false? So, what is an example of an unsatisfiable formula? Trivial. X and not X. Yeah, X and not X, right? So X and not X can never be, and this can never be satisfied. No matter what I set, this cannot be. Okay, so this is one example, and so this is what we want to check. Okay, so suppose you want to check that for any input. So now, in the way I have set things up, I want to say that sat and unsat are kind of equivalent to one another. And why is that? So I can reduce from sat to unsat in a trivial way. If I,
can invert the whole Boolean expression and ask if it can be satisfied.
Yeah, so what he's saying is that, suppose I have an oracle that can solve unsat. Okay. So that oracle takes some formula and can solve unsat on it. Now I want to solve the SAT problem. What is the SAT problem? I'm given phi, so I want to know if it's satisfiable or not. What I can say is, I'm going to invert, I'm going to construct a new formula that is not phi. This is another Boolean formula. Right? And I'm going to give it to that guy. And if that says that it's unsatisfiable, then it means that there's no assignment that, do I even need to give it not phi? Yeah.
Yes.
Yeah, you just give phi.
Unsatisfiable.
Yeah.
If it is, it's not.
So you don't even need to give it not phi, because that's yeah. Okay, so in fact it's even more trivial than what he said. Okay, so you just give phi to the unsat oracle, and this machine will do some computation. It will tell you if it's unsatisfiable. If it's not unsatisfiable, it must be satisfiable. So you just negate the answer. Okay, so that's the right way to reduce. You can easily see that the opposite would happen. So in some sense, intuitively, these problems are the same difficulty. I can solve one, I can solve the other. Let's see a slightly more involved example. Let's look at the matching problem. So let's recall matching. So you have a graph. What is this problem? We have a graph. So we saw this at some point. Graph of students, potential partner, project pair. Okay. So I don't know if you guys remember. So you have a whole bunch of students. Each one is a node in a graph. There's an edge if these two are willing to collaborate on a project. Okay. So a person may be willing to collaborate with multiple people. You could have a graph like this, and we need to answer, want to find out if there exists a perfect match. i.e. matching that pairs everybody. So how would you reduce this to SAT? What does it mean that you want to reduce this to SAT? So remember this picture, right? So if I want to reduce problem A to problem B, you would assume, suppose there's an oracle for B, then I can solve it. Right? So how will you do this? So this is A now, this is B.
So here the Boolean variables will have would be whether a particular project is assigned to this a specific student, and we need to take.
But what do you mean by particular project? Now we don't have projects, and we just have students, and we have possible.
So a particular student is paired with another student, so we have n square Boolean variables.
Okay.
And we want to check whether the conjunction of all this, so there must be one pairing which
Yeah, so but what you're implicitly trying to do is you have an oracle for SAT, right? So this takes a formula phi, tells you if it's satisfiable or not. Now you're given a graph G, and you want to know if there's a matching or not. You're trying to implicitly construct a formula. And constructing a formula means you've got to have some variables, you've got to have some constraints, right? So that's how you should be reasoning. Okay, so what are my variables? What are my constraints? Right. So variables is what he said is correct. Right. So the variables are is student I paired with student J. Okay, so you've got n squared variables which I'll call xij. So these are legitimate variables. Right? So what are all the constraints now? It's always better to write down constraints in English, and then you can convert them into math. Right? So what are the constraints intuitively? Yeah.
So at any given point of time, all the students should be paired
Okay.
in any arrangement.
There's no point of time, and at the end of the day, all students will be paired. Okay. So in the final assignment, every student must be paired.
Every student must be paired. No student should be paired to more than one students.
Students. Every student paired to. You can combine these two and say every student is paired to precisely one other student. Good. Anything else? Yeah.
There should exist an edge between I and J.
Yeah. So if you pair if we pair I and J, there exists an edge. This is it, right? So any instance you can write it like this. So this is like saying I'm only allowed to pair students for which there is an edge. So right, so now how do we make this mathematical? So actually what is an easy way to deal with this problem?
Only include xij's in our final formula if there's an edge in the graph.
Yeah, so one thing you can do is just throw away all xij's where ij is not an edge, right? Because that's not even allowed. Okay, so only have. Okay, so maybe I should have a new page for this. Okay, so. So let's give names to these. Okay, so 1 and 2. So this 0 is part of 1, right? Because I said it's precisely one of the 2. Okay. So I just need to satisfy 1 and 2. Satisfying 2 is easy. Okay, writing down dealing with 2 is easy. Only include variable xij if ij is an edge. Okay, so how do we deal with 1? How do you now write this fact that every student is paired to precisely one other student as a constraint? Yeah.
If we take if we take I as 1, so we must have x12 or x13 or x14. Maybe or all of them, and that should be 1.
Okay, so this is attempt 1, right? So if I take for any I, okay, I look at all j's for which this variable exists, okay, and I say that suppose neighbors are j1, j2 up to some jk, then you're essentially saying that I want xij1 or xij2 or jk equals should be true. Right? and this must be true for every I. So this is certainly fine, but does it encode exactly what we want to say? We want to say that every student is paired to precisely one other student. So how does an OR?
Yeah, it won't be precisely.
Okay, so yeah, so how do you get rid of this? Yeah.
So once you pair a student, you get rid of all the other edges that are associated with these two students, and we don't consider.
But this is not an algorithm, right? So you want to just, so this is the thing about reductions. So you've got to come up with one formula, okay, which is going to capture all the constraints you want to capture. Right? So you can't say, oh, suppose x1 was set to something, then I want all the rest of the guys to be zero. Is there a way to encode that in a formula itself? Yeah.
You can like mark all the ij's that are already taken and include xij.
But what do you mean by things that are already taken? There's no, I mean, you are just, so the idea is you're just given one shot, right? So you have to come up with a formula. The formula should ensure that you are not mapping things to this. Okay? So if you didn't have Boolean restriction, right? So if you didn't have to write a Boolean formula, one way you could write is, I want xij1 plus xij2. You could write a literal constraint that says xijk equals 1. Right? And this would exactly capture what you want. Right? But the point is, we are not allowed arithmetic, we are only allowed Boolean things. So, sorry? But and can be 0, right? So if I have
So if there is an edge between I and J1,
yeah,
I and J1, and if there is an edge between I2 and J2,
okay.
and if there is an edge between I3 and J3, then only you equate it to 1.
So there's no equating it to 1 because
I mean, or how many number of edges there can be like in such a graph? How many parents there can be?
okay, so this is a valid formula, right? So what she's suggesting is, I look at all the matchings in the graph, okay, all potential valid matchings in the graph, and I have one constraint that says x I1 J1 and x I2 J2 and such and such, and then you have an OR of all of these matchings, right? So for different matchings you have. So what's the issue with this though?
It's not polynomial time.
Yeah, so the size of the instance you come up with, if there are exponentially many matchings, then you will end up with an exponential size formula. Okay? That's not what we want. We want a polynomial size formula. Right? So this is a perfectly legitimate way to write down this problem as as something like this, but I want a polynomial size way of writing. Right? So the hint is, suppose I just take this equation and I want to make this one polynomial sized Boolean constraint. How would you do it? Yeah.
Sure, this will be wrong, but the above formula we could do xij1 and not of the rest.
Yeah, so this is what's called, I was hoping somebody would come up with this inclusion-exclusion type thing, right? So you can say that, so suppose, actually, let's take an easier problem. Okay, so let me just want to write a Boolean formula for, so y1 plus y2 plus so on up to yk equals 1. So this is a arithmetic formula. Suppose I want to write a Boolean formula for this. One thing that he's suggesting is I could say I have y1 or yk. So this must be true, and also so actually the intuition I think comes from the fact that suppose I had k equals 2 or something, right? So if I had k equals 2, then you want to say that you want to include y1 or y2. You must also have and of y1 bar or y2 bar. Because if both are true, then you must exclude. Right? So you want to say that 0, 0 and 1, 1 are not possible, right? So if I just had two things. So basically 1, 0 and 0, 1 are both allowed. So you can write expressions like this, but you'll easily see that if you try doing this, you'll end up with 2 to the k many constraints. If you try to say that, oh, I must have one of these things and I must not have any 2, then you have to exclude things where there are 3 and so on. Okay? Then you will end up with exponential in k. And k could be big, so this is again an exponential graph. Is there a slick way to say that, inspired by this, is there any slick way to say that, because remember all you're trying to say is, if I pick one, I don't pick the other guy. So, is there some way to say this? Sorry? Sure, that's the Boolean thing, but what would you say? What would be your constraint?
If we have one such kind of arrangement, all other arrangements are not possible.
Correct, but how would you encode that as a formula, right? So if I just have variables x1 through xk, I want to y1 through yk, and I want to say that precisely one of them is true, right? So how would you,
I would guess something like y1 and then not the rest of them, or y2 and not the rest of them, all the way to k.
So this is so this is one way to write this. So
Could
you
be
can
k
say
formulas, k
y1
k squared.
and not of y2 or y3 or k, or y2 and not of y1 or y3 or. So this is a nice way to write this, right? Because what you're saying is, so if this entire thing were satisfiable, then it's an OR of a bunch of terms. If the whole thing is satisfiable, then one of these terms must be satisfiable. Each term looks like this. Each term is essentially saying, I must have y2 to be set to 1 and everybody else must be set to 0. So this is one way to encode the constraint that y2 is 1 and everybody else is 0. Okay. So there's another way to do it, which is basically saying I have OR of all of these and then I exclude any pair of them being equal to 1 simultaneously. So that will also be something like k squared. So this is a simple exercise for you. So you could say I have y1 or y2 or yk. And I also have AND of y1 bar or y2 bar. And of all these things, right? So all pairs. And now I have k choose 2 different pairs out here. And this is again a k squared size formula that captures. So, right. And in your Sudoku homework, you'll find that essentially this is what the solution is. Okay, so you just have a bunch of constraints. You just want to write them as all right. So this is just an example to tell you that we'll get to that in a minute. So I just want to give an example that reductions are often tricky, right? So you can't think algorithmically. You can't think that, oh, suppose I had set this to 1, then I must set all these other things to true. Because in some sense you could have this one-shot formula that you give, and the proof should say that if this formula is satisfiable, then there is an assignment or there is a matching or something like that. So that's something to keep in mind. Okay.
But even in this case, even in where we are saying y1 and not of y2 or y3, we are still calculating different arrangements like y2, y3, y3.
Yes, but it's a polynomial number, right? So suppose I consider this thing. Okay. So actually, what does these dots mean? So I just essentially have yk and not of y1 or y2. So this is the formula, right?
What is k?
K is a number. So k, you have variables y1 through yk. Okay, and the point is that here you had this constraint, right? So each, I mean xij1, instead of writing it out every time, I'm calling it y1. xij2, I'm calling it y2 and so on. So this is just to simplify notation. I'm just saying, suppose I had to write this one equation as a Boolean formula, then what he said is essentially that this Boolean formula captures that one equation. And that's what we are trying to argue, that if this is true, that is true, and if this is false, that's false. So questions? Okay, so yeah, this is, in some sense, this is more of an exercise on how to write things as Boolean formula. Okay, so it's just that if you have arithmetic, sometimes things become simple. All right, so this is good. Any other questions? Okay, so what have we shown here? We have shown that now you can do this for every I, and now you take an AND over all I. Okay, so that's the final formula. Okay, the reduction we have is it takes an instance of size n, and the other thing is polynomial. Okay, it's something like n squared. Okay, so actually it's more like n cubed, because you have n squared constraint for every I, and therefore the overall complexity is like n cubed. Reduction size. Okay, so so you've mainly got to verify that this is polynomial. Okay, so that's the key. Okay, so any polynomial is fine, but it has to be polynomial. All right, so these are what I call Turing or Cook reductions, right? So what you've got to come up with is you can use function calls to the problem B, and you've got to come up with an algorithm for problem A. So last time I said that there's something which is slightly subtle here, which is you could also say that I want reductions where I transform one instance of a problem to one instance of the other problem. So this is what we did in the matching case, right? So we said that I started off with a matching instance of matching. I constructed an instance of SAT, and I said that if IA is a yes instance, IA is a yes instance for A, if and only if IB is a yes instance for B. Okay, and we showed this. But if you think about it, in the first example that we saw, in like the reduction from SAT to unsat, we did not do this. Right? So we said that you come up with this, you give the unsat oracle the same formula, and you negate the answer that you get. And that negation is not allowed here. Okay, so here we are saying it's a yes instance for A, if and only if it's a yes instance for B. So as I was saying, this is kind of a subtle point here. So it's like a yes maps to a yes. Okay, you're not allowed to map a yes to a no. as we were doing in the earlier. So intuitively that sounds like a perfectly valid reduction, right? So like I give the same formula to unsat, if not I negate the answer, and both the problems are equally difficult intuitively. But in terms of carp reductions, actually this is not what we do, right? So these are, I'm not constructing one instance for unsat such that the answer to that is the answer to this. So that's something to keep in mind. Okay, so this is how the first reduction we showed earlier was not a carp reduction. So carp is a person, for those of you who don't know. Okay, so it's something that he had proposed. Okay, so and you transform yes instance to yes instance. So you might see this is restrictive, right? I mean, why isn't the previous thing a legitimate thing? And it is a valid concern. Okay, so there's no right answer to this. It's just that complexity theory becomes nicer if this is the definition. Okay, so that's the best answer I have. Okay, so you get these classes called co-NP and NP, which kind of have their own significance, and yeah. So in some sense, complexity theory becomes nicer if this is how you define reduction. Okay? So whenever we talk of reductions, we mean reductions of this kind. Okay, we mean carp reductions, where you're given, you want to show that problem A can be reduced to problem B. What you've got to do is take one instance of problem A, come up with one instance of problem B, and you must argue that this instance is a yes instance for A if and only if IB is a yes instance for B. So this is what we call instance transformations. So you take IA and you transform it to IB. So you can think of like the problem A as having a whole bunch of yes instances and no instances, and this is like saying all these guys map to the yes part of this. They may be mapped to a very small yes part, and all the no guys map to the no part. So this is what we are talking about. Okay, so this is what is called a carp reduction. As this is a subtle point, maybe some of you will have questions. So, any questions on this? Yeah.
So, it's like, are there any other options possible apart from yes and no? So, what do the other instances of A and other instances would be comprised of? That do not
No, for A, it's everything is yes or no, right? So both are yes no answer. I mean, are you asking in this picture why is this going to a smaller set of things?
Yeah.
Yeah. So I mean, so B could have. Remember, like here we transformed this graph problem into SAT, right? But the results you get, I mean the SAT instances you get are only of a special form, right? They're only formulas where you have stuff like this. There are other SAT instances in the world which never appear in this reduction, right? So that's why this need not fill the space for B. So I mean there are other yes instances for SAT. Some of them don't have a corresponding matching instance that would have given rise to that. Yeah.
But then what if that would make I be like a universal thing of satisfiability?
Yeah. So that's the picture. So the picture for A is so this is problem A, right? Problem A has a whole bunch of instances, right? Every instance either yes or no. That's that. Problem B has its own set of instances, okay? And I mean both are infinite sets, okay? So the picture is kind of misleading probably, but what we want to say is that instances of A, the yes instances map to yes instances not. There could be other yes instances.
Can every Turing reduction be made into a carp reduction?
No, in fact, that's the big question. Like, in fact, this for NP versus co-NP, we don't know if there's a carp reduction from SAT to unsat. Okay, so this is one of the big open problems in complexity. Like, does there exist or vice versa. But, I'm sure if one direction exists, the other direction has to exist. But yeah, so this is one of the big things. Okay, so this is one reason why these kind of reductions are interesting, because somehow there is a certain meaning to asking if yes instances map to yes instances, and that kind of gets lost in Turing reduction. So yeah, but this is a great question. So we don't know if there is Karp reduction. Good. So yeah. So this is a subtle point, but it's something that you should be aware of. That in reductions we always transform yes to yes and no to no. So now, what are NP hard and NP complete? Is there a difference? And so yeah, people have seen it before. So actually, yeah, NP. So what are the formal? I just wanted to give out the formal definitions because it's something that always comes up. So what is the definition of NP hard? Yeah.
I think it's defined as being at least as hard as all problems in NP, or at least as hard as the hardest.
But an easier way to define it is by saying at least as hard as SAT.
Okay.
Okay, so which is like saying problem P is NP hard. So actually P is a bad notation. Problem Q is NP hard if SAT reduces to Q. And actually this is what I'm going to write. Okay, so this is, I don't know if I've introduced this notation here. Actually I forgot to introduce this. But we'll always write less than or equal to with the subscript P, because the subscript P indicates that it's a polynomial time reduction. And if SAT polynomially reduces to problem Q. And by this we mean exactly this. Okay, so for every instance of every yes instance of SAT, I can map it to a yes instance of that. So this is like saying, and I wrote the less than or equal to because it captures this notion of SAT being easier than problem Q. Okay, so that's why I write less. So at least I find this a bit easier to conceptually. Alright, so that's what we mean by NP hard. Okay. What do we mean by NP complete? Yeah.
Doesn't this definition imply that Q is, there's a Turing reduction for Q to SAT, right?
From SAT to Q.
SAT.
Yeah, so as you were saying, right, so every Karp reduction is obviously a Turing reduction. Because Turing reduction, you're allowed to make many function calls to your thing, and you're allowed to do anything with the answer. Okay? So a Karp reduction is only a very special case of this, right? You take one instance, you come up with exactly one other instance, you send that to the oracle, you report the same answer that it has given. Okay? So every Karp reduction is obviously a Turing reduction, but the other way around is not known to be true. Okay, so yeah. Does that? Yeah. Okay, so and when I say less than or equal to P, I always mean a Karp reduction. And as I was saying, the reasons for this are kind of pedagogical. This creates interesting complexity. Alright, so what is NP complete now? Okay, so it's basically both directions. Okay, so it's Q is NP complete if Q reduces in P to SAT and SAT reduces P to Q. My task is Q equal to SAT, but it's not, right? So you could you allow polynomial blow-ups and all of these things. So we'll see example. Okay, so So yeah, so this is something to keep in mind. So where people often throw around these words, so you should know what it means, right? So NP hard. So this statement is also, sometimes people say that the problem is in NP. Is in NP. And if it reduces to SAT. Okay. So remember, I defined the problem to be in NP if there was this non-deterministic Turing machine or whatever. Turns out that that is equivalent to saying that Q is reduces to SAT. And this is what is called the Cook level here. So this is actually a non-trivial fact that these two things are equivalent. The problem is in NP and that Q is. But you can assume for now that it's true. So a problem is NP complete if it's in NP and if it's NP hard. So that's another way of saying it. Or yeah, you just have reduction both there. So you could ask, are there problems that are NP hard that are not NP complete? So any guesses? Like, are there super hard problems? I mean, intuitively the answer is yes. Right? You have like an extremely difficult problem. I'm not telling you what the problem is, but you could imagine that it's harder than SAT and it's harder than anything you can imagine. But and that is NP hard for sure, right? And but maybe the other way around is not. So typically games are like this. Okay, so where you've got to determine, for instance, suppose I ask you, does chess have a winning strategy for white? So, and if I have a problem like this, then these kind of problems, you can't quite write them as SAT formulas. Okay, so you will have an exponential blow up if you try to write them as a SAT formula. Because, so there's a back and forth, right? So what does it mean that it's a winning strategy for white? It means that no matter what, I mean, there exists a first move such that no matter what the second move is for B, you end up with a winning thing for A, and this turns out to be complicated. So you can't write this as that. Or at least we don't know. Okay, so there are problems that are NP hard but not NP complete. Okay, so this is small picture, right? So it's yeah. So NP is this class of problems. P is a small set of it. This is how we believe that the world looks like. Okay. For all we know, everything could be equal, but actually not NP. There are halting problems that's not NP, but for all we know, this whole thing will be the same. But we believe the world looks like this. Okay, so there's some problems that you can solve in polynomial time. Some problems that are NP complete, and here satisfiability and all these problems come in. Okay, we've seen this. And yeah, a bunch of everything we've seen so far in this course comes into P. Okay, and we are going to see stuff like this too. Okay. And interestingly, there are problems that are not going to be either. Okay, so, and factoring is one such problem, graph isomorphism is this other problem, which, I mean, they could be in P, but we have strong evidence to think that they are not NP complete. Okay. So that's interesting. Okay, so this is one picture. And again, this is a more complicated picture, right? So complexity is a very well-studied field. So people have defined all kinds of complexity classes. So like P is one of them. There are classes that are much more tight than P, and there's NP intersects that, but there's all other overlaps and so on. Okay, so complexity theory is a very messy area. I mean, it's very beautiful, but the links are complicated. That's a good way to put it. Okay, so that's, so this is how the landscape of problems looks like. So but our concern will be things that are simpler. So next time we'll see examples of this. So we'll see how you actually construct reduction. Okay, so we've seen one example today from matching to SAT. We'll see examples of SAT to other problems. Okay, and that kind of shows NP hardness and therefore NP completeness.